Well, hello everybody. Welcome to my next session in my Data Science with Mathematica track. Today I will be talking about JLink, that is an additional package in the Mathematica system that allows you to seamlessly interact with the JVM, the Java Virtual Machine. I had already started talking about link packages in Mathematica. In the last session I talked about liberating and link, and I had briefly mentioned Mathlink, or its newer name WSTP. And today I'll talk about another link package, JLink. So this is the package that allows you to interact with Java, or more precisely with the Java VM, the Java Virtual Machine. Under the hood, it also uses Mathlink or WSTP as well. And I find it insanely cool because this is bidirectional. You can call into the JVM from a Mathematica session, and vice versa, you can call into the Mathematica kernel from a Java or Scala program. I have used it ever since it came out, which was for Mathematica version 4.1, I believe. It basically means the whole Java universe is at your fingertips with Mathematica code, and vice versa, you can program in Mathematica from Java. And here I mean Java as a language, but also with all the other JVM languages, such as Scala, for example. With JLink, basically everything in the JVM, really everything becomes an automatic extension of Mathematica. And vice versa, Mathematica becomes an automatic extension of your Java or Scala programs. So in the first part of my session, I will be calling into Java, again more precisely calling into the JVM from Mathematica. When we say Java, we have to be a bit more careful because it really means two things. We have Java as a virtual machine, and we have Java as a programming language. So I will typically be referring to the JVM when I say Java, probably not the programming language, until we get to the second part, which is calling Mathematica from Java. Here I will mean the programming language when I refer to Java. And the part in which I call Java classes from Mathematica, I will split up into a section about non-visual classes and about visual classes. I find both types of applications just incredibly useful and powerful. So okay, let's jump right in it. First, we load the package. So we do that with a needs command. And I personally always want to use the latest JVM that's available. That is for reasons of performance, for bug fixes, new classes that became available. And as of March 17, that is version 14.0. That is the latest Java release that we have. And as a footnote, I refer you to two articles here that describe new features in Java 14. We now have switch expressions, we have text blocks. There's a new class, the record construct, that allows you to make record management much easier. Before you had to write your own classes, and things go now much easier with a record class when you have, for example, a record of personnel data or a record of whatever type of data that you want to collect that represents a data record. Okay, so in addition, I also set some non-standard options for my settings, and you can do that with set options. You can define the command line and the JVM arguments directly here with JLink. I point out that reinstall Java under the hood needs install Java, so don't leave out the second line in which we set options for install Java. So I'm going to the latest Java installation here. These are symlinks on Linux. This is always getting updated, so I really never have anything to do here. This automatically gets me to the latest Java. And then I set some memory options as the JVM arguments. I want 24 gigabytes for standard and maximum memory. Okay, so I will set these, and then I need to run reinstall Java, otherwise it doesn't take effect. And now I have Java 14 that is used through my JLink session. Personally, I like the Nimbus look and feel the most, and I wouldn't execute the following session if I didn't have to deal with Windows, but I will be using a lot of Java Windows today, and that's why I just want to change the Nimbus, want to change the look and feel to be the Nimbus look and feel. And next, with Show Java Console, we can verify if we are using the correct JVM. This is the definitive way to check if you are using the Java version that you want in your jailing session. So here we have the Java console, and we can clearly see we're using jailing version 4.9.1 and we're using Java version 14 on a hotspot 64-bit server virtual machine. Okay, so we have verified we're using the latest version here. While we're at it, I also want to point out that we can also use this window now for messages. We can print to system out, and we can also print to system error. You see that we capture system out and system error here. We can clear it. It's a very convenient console window basically. It's the Java console, except we have a separate window for it that comes for free with J-Link. Okay, so let me just print something to system.out. Hello from the Mathematica frontend. This is a message sent to system.out. We see this here, and I can also print to system error. Yeah. Hello from the Mathematica frontend. This is a message sent to system.error. And it has scroll bars, so if I print a lot to it, for example the first 100 Fibonacci numbers, you see that we're automatically getting scroll bars here. Quite useful, automatically done for you. I find this a very useful window for printing information and for debugging and for interacting with Java directly from your Mathematica session. We can also query versions directly. We can look at the J-Link information, that is 4.9.1. We have the version number is 4.9 and the release number is 1. So this confirms the information that we have up here in the Java console window. Okay, so next, one thing you will probably be using quite a lot is reflection. And it functions similar to an IDE's IntelliSense. We can inspect what methods, classes, and constructors and fields we have for an object. So for example, here let me create a Java string that just says hello, and we see that in the Mathematica frontend with these double brackets, and it says Java object, and it tells us the type, tells us the class of this object. It's a Java language string. And we can now inspect the methods by just calling methods on this string object, right? We now have an object. Java new creates a new object that is functioning like a constructor, and we can look at all the methods in this object just by calling methods on it. And here you see everything that would be available in an IDE's IntelliSense, right? These are all the methods that are available for a Java string. We can filter out, for example, here are all the getters and the converters that we have here. We can look at the fields. We can look at the constructors. This is basically the same type of reflection that you can have in IntelliSense. And Java error messages are printed directly to the regular Mathematica message output. So for example, if I call something invalid here, I get the Java stack trace directly included here in the Mathematica frontend in the normal message dialog. And I want to point out the mechanism by which J-Link works is really by providing pointers to the Java runtime. This is really important to emphasize, right? We're not using the Java language here. We're using the Mathematica language here. But it works by having pointers into the Java runtime. So that means we have the entire universe from all the classes available. And this may sound trivial, but it's really a profound statement. Don't think about this as Java code, right? We're looking at Java code later on. but these are really just pointers into the JVM. So here I load a class that I use for formatting a decimal number. Here I use the Java text decimal format class, and here I specify the format that I want to be using. So now I can use it on what in Mathematica we call a real, and here I have 1 digit in front of the decimal and I have 7 digits after the decimal, right? This is pi with 7 digits, 7 decimals. And the number is now a string, but that doesn't really matter for formatting purposes. When we are talking about formatting, we convert many things to strings. And if we then use functions like export or write, then these operations don't really care if the string it writes is actually a number. It doesn't care, and it doesn't know. If it says hello or if it says a number, then it doesn't care. And I find this incredibly useful when I write a lot of numeric data into CSV files. I want them to be formatted properly. I want them to be formatted with the same predictable number of decimals. So this is what I use in order to turn my numbers into properly formatted strings before I export or write them into CSV files. I find this quite useful. So the runtime itself provides plenty of useful features. So let's load it. And I have to point out, when you're using static classes, we have to use the backprime here. We use the regular dots when we have these object classes, when we instantiate from them, like with the new constructor. And we have to use the backprime with the full name, with the full class name when we're talking about static classes, but they don't get loaded automatically. So we always have to load the class first. So first we have to load the Java language runtime class, and then we can call a static method from it, but we still have to use the name. We still have to use runtime backprime and then the static method. So with RT we now get the runtime itself. So now we can use methods that we have in RT. For example, we can call the garbage collector, although that's usually not a smart thing to do. It's very rare that you explicitly should be calling the garbage collector. We can look at the number of processors that are available, free memory, total memory, max memory, and compare this to what we have in processor count. So $processor count is the number of physical cores, and available processors then is 2 times that using hyperthreading. And free memory, total memory, and max memory is now the Java memory. You remember that I used 24 gigabytes in my JVM options. So this is the Java memory, not the main memory, the RAM that's available. So we can now call several methods from the runtime itself, such as memory or query for different things. We can again verify the version numbers. We are using Java 14, the minor version is 14, the feature version is 14. We can inspect everything in the runtime class. We already have seen how to do that. We just call method on the object. So here we have all the runtime methods, and specifically if we go down one level for version, we have all the methods on the version method. So we have the first ones here and the second group here. Next, I think the file class has a lot of interesting stuff for us. So for example, let's look at the disk space that we have in the home partition. And I'm on Linux, so I use the / notation here. Home is the home partition. So I have usable space and free space of about 1 terabyte here. Total space is 2.7 terabytes. The disk space for the boot partition, I just say boot here, and then when I have these new file objects, I just call these methods, same name. Here we have smaller numbers for that. I have an external drive that is mounted, it's called 8, and it's mounted to the MNT partition. Here I get much larger numbers. Here I have 8 terabyte. And let's look at the disk space for root. And I always try to write things in an operating system independent way. And I think one way to do that is to start with an arbitrary directory and then always query the parent directory until it no longer changes. Now you're definitely at the root because the parent directory of root is itself. So now we have these free space queries for the root directory. And if we look at it, then it seems to be matching, right? We have 8 terabytes for my 8 hard drive. For the home partition, the 2.6 terabyte that we saw earlier, the used and available space. Also, we looked at boot, that was 1 gigabyte. We looked at root, that was 74 gigabytes, and so forth, right? So these numbers seem to be matching. So now, in the next part, let's look at the visual classes. So J-Link provides some additional classes that make it easier to handle Java windows directly from a Mathematica session. There's a lot of usefulness in that because we can do a little bit more than what is standard in Java when we assume we're coming with a Mathematica session, a kernel or a frontend. So in the following, I'll be using the math frame and the math canvas classes that come with J-Link. The math canvas is similar to the AWT canvas class, but it adds a method that allows you to directly specify a fragment of Mathematica code to display, and that's incredibly useful, and you'll see that in a moment. That can be graphics or typeset expressions. For more info on the math frame, the math canvas, and the math graphics JPanel, please see the documentation. And I should learn to spell canvas correctly. Sorry for that. Okay, so let's launch a new J-Link math frame. And this gives us a frame, and in Java we have to do a little bit of layout management, and there are several different layout managers available for that. I find it most useful to use the border layout from AWT, the abstract Windows toolkit. Then I create the math canvas again with a constructor using the J-Link math canvas class. Then I can set a title on the frame. It's important that you set a title on the frame, that's the window. Then I need to add the math canvas class to the frame. Otherwise I have a canvas without a frame. So this is the line that combines the frame with the canvas. Then I can set things like sizes. When I'm done with all this, I have to call the layout method so that all these layout methods take effect. And here comes the cool method. I can simply say set a math command on the canvas, and then the math canvas will show the output of this graphics or typeset expression. So let's do it. And we see that here we have this plot. The title is sine and cosine functions that I've set here. And I'm plotting the sine and the cosine function. We have them right here. Okay. And again, I don't want to beat a dead horse, but I think it's important to emphasize again, it lets you use all the features of a JFrame with everything, the title, the sizes, component listeners, events, adding, removing components. It has getters and setters. So if you're a Java programmer, you're familiar with all these things. And I want to emphasize again, you have all of this available, right? I'm just not using a lot. I'm using these something like 9 or 10 lines here. I'm not using a lot, but everything is available. If you call methods of frame, and I think I'm going to do this in a moment, then you see a long list of I don't know, 100 or 150 methods. So all this would be available, and we could now manipulate this. We could add components, we could add mouse click events, we could add menu bars. Everything would be available from your Mathematica session. All right, that's because the math frame inherits from the JFrame, so you get everything from JFrame. All right, and you now just need to set another Mathematica expression with the setMath command, and you get an updated display. So look at this. I'm not starting a new window. I'm using the same one because math canvas is the returned object and I saved it, right? I didn't just call Java new. The return I saved in math canvas. And now I just set the math command and you see that we're getting an updated display in the window itself. And the reason I find these Java windows so useful from the Mathematica session is because I can now use a window and just move it around. I'm not confined to having the output directly under my input. Very often, for example, in a financial trading environment, when you're trading fast-paced financial derivatives, you have to be very careful about your screen real estate, and you want to have a window at the right time, at the right spot. You don't want to be confined into having the output only directly after your input. So this is now a window that I can move anywhere I want, right? Not just here. I can move it to the monitor on the right. I can move it to the monitor below, and I can move it to the monitor diagonal southeast, right? I have 4 monitors here. So this gives me a lot of freedom. I don't have to look at the output directly in the code. Okay, so note that this went to the same window. I didn't create a new one. We only changed the display in the canvas, not the title, not the window. We just set a new math command on the same canvas. Okay, but we could change things. I can now, for example, I also have the frame, right? I stored the frame in an object. I didn't just call Java new. I stored the return in a frame, so now I can call methods on the frame. For example, set title. So if I execute this, then I've changed the title to 3 plot, right? So the next logical step would be to run it in a loop. And again, note that I just call the setTitle method on the frame, so this will update the title with a new title. And then I just loop over the setMath command where I'm splicing in an index I, and I constantly update it with a 1-second delay on the math canvas object. All right, so we do that here, and you see that I'm now pushing 10 new images, 10 new plots into this window that already exists. We changed the title and we're pushing 10 new plots onto the canvas. All right, so we can also display typeset expressions with a math canvas, not just graphic expression. So this one is rendered as a graphics expression. It uses the default for setMath command. So for example, when I do this, I want to compute the infinite sum 1 over n squared. That's pi squared over 6. So Mathematica computes this directly. When we say the sum of the 1 over n squared from 1 to infinity, then we are getting this output here. And I just use a hold form, a traditional form of a hold form for the left-hand side. That's why this sum doesn't evaluate. So I created a new window and I didn't change anything about the type of output. It's still a graphics expression, but we can change that. I can use the setImageType method, and here I have to use the mathCanvas.typeset. So again, this is static. We get the mathCanvas to typeset the return value. So you see here that I say my mathCanvas now gets the method setImageType, and the image type is mathCanvas backprime, right? This is static. And then I use typeset, which is a predefined constant. So when I do this, I get it in what we call standard form in Mathematica. Okay, so next I want to show you that we can do this with arbitrary Mathematica expressions. How about a grid? So when we use the next one, here I show you the 10 by 10 Hilbert matrix, and my function SM formats this as a grid with alternating colors every second row. And you see that we have a grid in our Java window. And this would now allow us to push live market data into a window. So I simulate this here with random numbers. We can just generate random numbers. Note that here I use a 10 by 10 matrix with a random reel, and I push it into a new math canvas that I set to image type math canvas backprime typeset. So this would now allow us to push live market data from a trading environment into our window, right? You see that I'm just simulating this with random numbers. I cannot use real market data. My online broker does not permit this. But instead of random numbers, let's go a few steps further. We can also use, for example, computed data that comes from live market data. For example, option prices. So in the following, I will simulate stock prices from a Wiener process and compute the correct option prices for that. And I generally prefer to use CUDA for something. I had given an introduction in the CUDA session, both in my data science track and also in the last session in my financial options track. So I load the CUDA package and I pick my device number 5. That's my 5th GPU, simply because it has the best cooling. But that doesn't really matter because the GPU doesn't even get out of bed for something so simple. I load the Black-Scholes code. You see this is a .cu file. So this is the file that contains the kernels, the CUDA kernels that we're going to use. Then I define my CUDA function. I call it Black-Scholes. I use 1024 as the block size. That's my maximum block size. And important, use target precision as double. And there's a few bugs in the package for Linux, at least for Linux. We have to specify the compiler installation specifically. So we try to load that. Again, there's another bug that causes me to load the line twice in Linux, but then it works. So let's create stock prices from $70 to $90 in steps of 1 cent. And let's create strikes from 70 to 90 in steps of 50 cents. Let's create these tuples and we get 82,000 tuples. Now when we compute the option prices, it's twice that much because in one swoop we're getting all the calls and all the puts. So we're actually gonna compute 164,000. So let's define this. We first compute the length of the tuples. We need that for the memory allocation. We allocate double precision for the calls, double precision for the puts. We take the vector for the stock prices, for current prices. We assign the vector of strike prices for strike prices. I take an expiration of a quarter year. We take 5% risk-free interest rate and a volatility of 50%. So let's compute this, and these 164,000 options, they took 68 milliseconds and we're done. So fairly fast, and that's the reason why I generally prefer to do more and more on CUDA, because it's instantly done. If you were to compute this with binomial trees, it takes longer and longer and longer, and I prefer to use CUDA as much as possible because you get computations instantly. So as the next step, we have to get the call prices from the GPU memory. We have to get the put prices from the GPU memory. I do some reformatting here. I like to have them as associations for very fast lookups. So then in the next step, let's generate stock prices for 5 minutes. So I take a time horizon of 1/12 of an hour. That's 5 minutes. That's 300 seconds. I start at $80 and use a Wiener process in order to generate this. I show the prices in a list line plot, and these are the prices that we're now gonna be using. So In the next, let's start again a new frame. Let's layout it. Let's use a math canvas. And here again, I will be using the image type as a math canvas back prime typeset. That's because I want to display a grid. My function sm creates a grid. And then I will just use all the stock prices here. I round them to 2 decimals. That's how I had done the computations above in CUDA, to 2 decimals, and we don't want to query any stock price that eventually doesn't exist. And then I just loop over this. This is a map here. If you look closely, you see that I'm mapping over this. So that causes me to constantly set the new stock price in the title. The set title method on the frame is part of the loop. And then in the canvas, I just create the updated options price table. So when we do this, you can see that we are ticking the stock price in the title, and you see in the call and put prices that we are getting the pre-computed option prices. The strike column is always the same from 70 to 90. So this is a simulation of how this would be in a live trading environment. The spot price doesn't always change that fast, but for some stocks it really does, and in particular for futures it does, and also for foreign exchange. The currencies and some futures, they tick like 50 or 100 times a second. So I'm simulating this here by going with the Wiener process generated stock prices, and you see instantly these updates of the call and put prices. And this is what a basic trading table for an options trader looks like. You have a strike column in the middle, you have the calls on the left, and then you have the puts on the right, and then you have further columns to the left and to the right? So the next column to the left would then be the call delta, call gamma, call theta, call vega, and also then to the right, the put delta, gamma, theta, vega. Right? I'm only showing these 3. This is more for proof of concept. A real trading screen would have additional columns, not just these 3. All right, so I had to mention it. You can inspect these methods. Now we can look at all the frame methods that we have, all the math canvas methods, and it's a long list. This is really everything that you would have in a Java IDE with IntelliSense. Long list of methods for the frame, but everything, right? Everything that is there, and that is quite a lot. Seriously, quite a lot. Everything that we have in Java, we have here now in the jailing session. Removers, setters, and here for the canvas as well, right? Adders for components, fires, Boolean queries, removers, setters. So everything available there. Okay, next let's verify the classes for the math frame and math canvas objects. So we see that we are using the math frame from the jailing class, because there is no math frame in Java. There's the frame, but for use from Mathematica it makes sense to have a math frame, and that's why that's included in the jailing package, and the math canvas as well in the jailing class. And the parent classes are the AWT frames, right? So as I said before, the math frame inherits from the AWT frame, and the math canvas inherits from the AWT canvas. Okay, so now we can also close them programmatically. I think I closed them already. Sorry for that. So you can also call the dispose method on a frame, and that closes the window to disappear. You dispose of the window. All right, so let's get a few steps further. In many applications, you want to display the result of a plot function, and that's any type of plot function. Plot, list plot, box whisker plot, dateline plot, whatever it is, other graphics generation function that pop up in a window. So, for example, you may want to keep the output, but you continue working in your Mathematica session. right? It's great to have it pop up in a new window so that you can push it away, but it's still there. It's good for comparisons. Generate several windows to compare and rearrange them on the screen. It's great for comparisons. Next, oftentimes it's important to have a particular window precisely at your particular spot on a big screen. Again, I mentioned a live trading environment. Then, because that's where traders have multiple monitors and all of them driven by the same graphics card, and they need to be able to move windows around and put them in precise spots with limited screen real estate. So it seems it would be ideal to have these plot functions generate these windows for us directly from within the plot command, right? We used a bit of code up here for these plots. Not the end of the world, but it's good to have them in wrappers and also generate new windows, generate these windows directly from the plot command itself, right? We want to be able to fire off different windows with a newly generated plot or graphics expression. Well, we have something for that. It's called the display function. Because all these plot and graphics functions, they have an option called the display function. So here I define a function, JDisplay function for Java display function. And I should probably not go through everything. Again, I create a frame, then I set a layout, I create a math canvas, then I set some options here, some window sizes, and in the end, I set the math command to be the string expression of the graphics expression in input form, and graphics GR was the input. Okay, this is really cool because in the next step, I can simply say display function goes to JDisplay function. When I do that, I get a new pop-up for this expression. So I get the plot just as we would get before, but I also have a new window with that expression. Now, if you don't want the output in the front end directly below the input, only in the new window, then you can simply suppress the output. And we know how to do that. Just add a semicolon and you ignore that it's in red here, right? You can redefine that in the options, but by default, Mathematica thinks there's something wrong if you want to plot something, but then not see the output. That's why this semicolon here is in red. It's not wrong, but it's unintuitive, right? Normally, when you want to look at something that you plot, but we are doing that, except we're doing it in the JDisplay function. So in this example, we get a new window, but we don't get the output here in the Mathematica front end. Okay? And we can do that for any plot function, not just plot. So for example, polar plot has the option display function. So let's use it. Here's a polar plot that we now send immediately into a new window directly from the plot command. Here's our polar plot. In fact, any graphics generating function is fine. We have the display function option also in show. So we can also use show on a graphics object, use display function goes to JDisplay function, and voila, we have the output in the front end. We could suppress it with a semicolon, and we do get the output in a new Java window. Okay, so I find this quite useful. I absolutely like it that we can create new windows directly from inside a plot or show or whatever else has the display function option. Okay, and let's get another step further. Sometimes we want even more features for window management. And if we use a lot of that, then I think it becomes sensible to not do it with Mathematica code that uses pointers into the JVM, but instead use it on the Java side. Keep it with Java code, because there is a certain degree of complexity that makes it very hard, especially if we want to do things like event management, handling callbacks, and so forth. You can do it, but it does become problematic when you want to pipe everything through pointers into the JVM. So if we use a lot of Java features, so code or inheritance or inner classes or event handlers, then I think it's better to keep that on the Java side, and that means written in Java, and now I mean Java as a language, right? And then execute it in the JVM. And we're not using J-link to call into the JIE directly all the time. Instead, we only call one time the final product of it. All right. So in the following, I use a couple of features that I have coded into functions that I called the JT window and the J-link utilities class. And if you write your own functions, or if you use Java libraries that somebody else has written, you may find them on the web, or they are sold commercially to you. Then you would put them in the class path, or you can put them in a location that you know and want, and then you just use the function add to class path. So my functions are now in a jar that I call J-link utilities, and by calling add to class path, I simply make this jar available for the class path. Next, I need to load it. The class is called J-link utilities, and it's a static class, so I have to call load Java class, and I want the statics to be visible. That's an option that we have in load Java class. It's not particularly important at this point. I just find it very handy. And now I have two functions. I call it JWindow and JWindow send. So JWindow creates a new Java window based on a Mathematica expression that we pass in, a window title, and a width and a height of the image. So this calls from the J-link utilities the static method JTWindow, and I keep the returns as a frame and a math graphics JPanel. And I want to use them after I am done, after the Java block closes. And the way to do that is to simply use the J-link function keep Java object. That means we're now telling J-link keep the frame. Even though we're closing the method, keep the frame. Let this get out, let this leak out, make it global, let it escape from the Java block. The same with the math graphics JPanel, and then I return them as a list here. So it will make sense that we assign this to a list of two expressions, otherwise we lose the references. That's why I specifically want to keep them, because in the next step I want to be able to send something to it. This is similar to what we have seen before with the math canvas, but I now want to use it with additional features that became so involved that I wanted to have them in my own class in a jar file, written in Java code, executing Java code. And JWindow send is now a function that allows me to send an updated math canvas to an existing window. But for that, I need to keep these references. So I need to load a frame and a math canvas, right? I call them send. Sometimes in Mathematica, we use the function put, like notebook put. Whenever we are sending something to something else, a new window, a new notebook, or a new cell, then in Mathematica speak, that's called a put. I wrote this years ago and I've called it send. If you think it's easier to remember, rename it and call it JWindow put. Perhaps that is more in line with Mathematica terminology. But the important thing is, so with JWindow I create a new one and display everything. Make sure we store in two objects what the return is, because we need those two in order to provide them to JWindow send as a frame and as a math canvas in order to send new ones. And we have to return the same thing, otherwise this syntax cannot be used repeatedly, right? We have to return a frame and the math graphics JPanel from a JWindow. We have to do the same with JWindow send. All right. So once we have defined this, then we can use it like this. And you see here I'm using the JWindow on a simple plot command. And note on the left hand side I store the references. It's very important now that we keep the frame reference and the panel reference. If I didn't assign it, then we would lose the references, and then we can no longer send or put anything into the new window. So here I have this window, and Another thing I want to point out, by default in JT window, I set the option to always have it on top. You see that I'm now clicking in the Mathematica notebook and this window doesn't disappear, right? So I find this useful. You can get in the code and delete it, but I find it useful to have this option, right? Some windows I want to disappear if I click on another window above it, and some windows I really want to be on top, like for a financial trading environment. That's my background. And you see that I now can click here in the Mathematica front end and this still stays on top. You see that the layer always on top is selected here, right? That's a simple property that you set in the window, and I have that here in the Java class. I'm going to show you this in a moment. So it's a simple choice that I like to have for some types of my windows. Okay, so now this is on top, just the way I want it. Okay, next I want to have the secant function, please, and give me a title. You see this one here has no title. Give me a title and give me an image size of 6000. All right, so we create a new window. We call it again with JWindow. We store the references, that's important. And now I have secant function here and I have plotted it and I have a plot size of 600. And one of the features that I have implemented there is that you may not think it's very powerful, but it was easy for me to do once I was in the Java code anyway. I sometimes like it when I can just make a copy of my window, because I may want to have it somewhere else on the window, or perhaps I want to make comparisons. So with this class, I can just right click anywhere in the window, not in the title bar, right? If I right click here, nothing happens. But when I right click here, then I get a new window that pops up with the identical contents, and it says copy in the title bar. And I can do this as many times as I want, but it has to be on the original window. So if I right click here, nothing happens. But if I right click here, I get a new window, right? And again, a new window. So now I have 3 copies of this. All right. And we store away the reference, and now I can use JWindow send in order to send an update into it. And you see that this has now received an update. I'm now plotting the sign function. The copies are still the same here. Okay, so I've added a feature there to use mouse buttons 2 and 3. So 3 is the simple right click. Mouse button 2 is the wheel that you have in the middle to make simple copies of the window. I find it quite useful and it was easy to do. This would be much more difficult to do if you did it from the Mathematica side. Here it's just easier to do it with Java code and keep it with Java code. Okay, so this would allow me now to keep an old version of the window and something new that I want to push into the window for comparison. So here, after the copy, let's plot the sign function, but with double the frequency. So now I have this here with double the frequency. Okay. And I said before, we have everything from the Java objects available. So that means we can now inspect things and we can modify things, right? So let's dispose of them. But when we do this, we can now, for example, query for the x coordinate. So this will give me the x coordinate. I move the window and I get a new x coordinate. I want to see the y coordinate, okay, 226. Move the window, get the y coordinate, 501. Okay, let me know the title. So I query for the getTitle method, sign function with double frequency. All right, so then next, set the title. I'm now changing it to a trigonometric function. Here is our trigonometric function in the title. Let me know the location. Okay, here I have the location. I can move it, right? Move it to the point 100, 600. Okay, now it's here. And I can do this from anywhere I want. I move it to 100, 600. I can go off screen, right? I have it now on the rightmost and bottommost window. Move it back to there. There we are. Right? Resize, make it 500, 500. Okay, that looks a bit crazy now, but I can resize it. Add a menu bar, right? I can just call this set menu bar. You see there's a new menu bar here. Okay, I would now have to fill it. I'm not gonna go through all this, but I can now add menu bars. I can add pull down menus. I can change mouse behavior and so forth. So inspect the methods, and again, I know I sound repetitive. I can simply look up what are the methods and classes and fields and constructors that are available. So long list of everything that we have there. So next, how about a price chart? So let's again simulate a Wiener process, and we get a price chart here. And how about a dateless plot for Amazon? All right, we're now retrieving the data, and we're now getting a new window that gives us Amazon for all of 2019 and 2020 so far. Okay, and again, just right click, get a new window, or the Wiener process window, right click, get a new copy of it. All right, so now let's query for the airlines and give them in a new window. So this gives me now a larger window, and I see a price chart of the airlines. So we can clearly see that the passenger airlines all have taken a diving here. And what I find interesting is that UPS really didn't tank at all from the cargo airlines. We see that FedEx and Atlas really took a dive, but UPS did not. Right? Again, copy if I want one. All right. So this causes me to leave now the what we typically call the windows, and a specific class of windows are the dialog boxes. And I'm a big fan of good modal dialog boxes. A dialog box allows you to branch out into different execution paths in your Mathematica code based on the interactive input from the user. And in Java, we have the J option pane. That's a particular class in Swing, and it has become a bit of a workhorse for me for those things. So here I'm defining a function modal for a modal dialog box. I'm loading a JFrame from Swing. So this is not from one of the J-Link classes. That's a standard Swing JFrame. And I also load from Swing the J option pane. So here's a static method, show method dialog. It needs a parent window, and we give that here as my frame. And then I'm not going to go through everything, but I have included a switch statement. Again, this is Mathematica code, not Java code, that based on the type, I can now display an information message, a warning message, a plain message, or a question message. And I use the error message as a default. So when I have defined this, I can now use this modal function for dialog boxes for interactive input. So for example, if I use info here, then, and again, note this is modal, so this is on top, right? This is automatically on top. So I'm clicking around in the Mathematica frontend here, and it doesn't cover the modal dialog box. So I use info here, so I now get an I for info in a blue symbol with info text and info title as the title. And this will look very different based on the look and feel, but I have already picked the Nimbus look and feel at the beginning. So if I use plain, this will look differently, but it will have the same logical elements. It's just the look and feel that will be different. It will function the same way. Okay, so the only way to get this away is to click it away. I can use a warning window, and if I use a warning, then I have an exclamation mark and a yellow triangle, warning text. I can use plain text, and this looks rather, well, plain. And there is a question window, and here we are getting a question mark with a symbol, right? So this is perhaps not quite as useful with just an OK button, but we will be using the question type modal dialog box in a moment. And the default is error, so that way we get an exclamation mark in a red octagon. So this is useful for visual error messages. I don't get tired of pointing out that in Swing we can use HTML formatting, right? So here's one, an info message, where I use HTML here in the text in order to display it in HTML formatting. So for example, here's our line breaks. Here I changed the font color to be red. Here I change it to boldface. Here's a color green. Here's a background, and then it will display that way, right? That means we can now use colors. We can use boldface. We can use colored boldface. We can use italics, change font sizes, or use strange backgrounds. So I find this very useful. The fact that we can use HTML formatting in Swing components, I think, makes it very easy to make very well formatted expressions and windows. All right. So, as I had mentioned above, the Java parts are getting too involved sometimes, and I like to keep it on the Java side rather than have it on the Mathematica side. This is all in Mathematica here, right? The entire modal function is Mathematica. It's still okay. I think this is not too complicated, but for what I'm about to show you now, this would get too tedious for me to do in Mathematica, so I write it in Java. All right. Mind you, J-link interactions really are Mathematica code. The programming language is Mathematica, not Java. We're just using pointers into the JVM. And for more involved things, I just want to call the finished product once. So in my J-link utilities class, I now have a function option dialog that I wrote. And if we use this, we now get some more involved dialog boxes. For example, here, this is a very simple option dialog. We get buttons in that case, right? So what's your favorite city? Now, based on what I click, Seattle, Denver, Pittsburgh, we're getting that result. So let me click on Seattle and we're getting a return of 2. If I click on Denver, we're getting a return of 1. If I click on Pittsburgh, then I get a return of 0. And I want to point out, see the last argument here, that's the default selection. And Java is 0-based indexing, Mathematica is 1-based indexing, right? But you can change that with appropriate wrappers, again, either on the Mathematica side or the Java side. So when I have 1 here, it's really the second choice, because 1 is the second number in a 0-based indexing. So Denver is the push button that is highlighted because it's the second element, right? So we automatically get a default choice here. All I need to do here is click return. I don't even have to use the mouse to click a button. All right, so the default element, the last parameter, is 1. So we see that Denver is the pre-highlighted button. The indexing is 0-based, not 1-based. So you have to add one more, or you change that, right? You can change that here, or you can change it on the Java side. So we can now further process this return from the user and branch in our Mathematica code. So for example, with the switch statement here, right? Based on the return of this option dialog, the switch statement branches now. So if I now say Pittsburgh is my favorite city, then the Mathematica code branches and says the user selected Pittsburgh. If I use Denver, then I get the user selected Denver. If I click on Seattle, then we get the user selected Seattle. Okay. So now I've implemented a few more, for example, a pull down dialog. So here's the question, what is your favorite animal? And again, note the default. Note that I have a 2 here. So that means the pre-selected choice is the third one. So horse is pre-selected, and that's the third choice, right? In the pull down, you see that horse is pre-selected to be the third choice. So today my favorite animal is the wombat. I click OK and we get wombat as a return, right? If I say cancel, then we have no return here, and we would have to handle that one appropriately as well, right? Again, note the default to source is pre-selected. How about a long list with a pre-selected default? For example, a printer selector. Again, note here my default is number 3, so number 4 is pre-selected, and we see that the 4 is already highlighted, right? In the list from 1 to 20, my 4 is already pre-selected. Okay, so today I like printer number 17. I click OK, we get the 17 here. How about textual input? I wrote one that I just call input dialog, and here we have a default choice that is already pre-selected. So if I want to use the 7th floor printer, I just take the default, we get 7th floor here. If I don't like it, say I want to take it in the mail room, then I write it in here and I get mail room as my choice for further branching in the Mathematica code. Then I couldn't resist writing a slider, so here I'm selecting a percentage, say I want 20%, click OK, I get my 20 here. Okay, so this is what I implemented in terms of dialogues. I can do more if you want. Feel free to download the Java code. The link is in the description below. So while I was at it, I've thrown in a few others that I thought were quite useful. So how about an interactively clickable swing tree of a Mathematica expression? What I would like to have is the ability to interactively explore the Mathematica expression and selectively go deeper in a selected branch of the nesting that I'm interested in. Right? This is somewhat a perspective of a depth first search, DFS, right? When you do a lot of work on trees, you know there's BFS, breadth first search, and there's DFS, depth first search. So if I want to start at the root node and go down all the way to the last leaf in a branch that is depth first search, I want to go deep first, not broad, not breadth first search. Okay, so I want to be able to zoom in and to focus and to drill down selectively simply by expanding and collapsing interactively my expression. And let's just look at a few examples for this. For example, I want to look at a plus b plus d plus pi in my JT tree. And we see that this is represented as a plus of a, b, d, and pi. Right? This is what this would look like in the full form, plus of a, comma b, comma d, comma pi. And you see that this is clickable. I can expand and collapse on this expression tree. And one thing that occurred to me at this point, we still have all the calls and the puts in memory from the previous computation. So, well, I can use this interactive exploration of my Mathematica expression, and I can set up a compound expression. For example, a simple list, right? If I want to look at 2 or more objects, then just throw them in a list, right? A list is a valid Mathematica expression. So here I now want to look at these calls and puts. So when I use this on a list that simply consists of the calls and the puts, then I now get a list of these 2 associations. The first one is the call association, that was C, and the second one is the put association. Oh, I see I didn't have any, I didn't give this the on top property. I can change that. So here's my call association, and you may remember the first one was the 70 strike. So here is the 70 with all these call prices for the 70. The last one was the 90 strike, and here is a list of all the calls for the 90 strike. Okay, and then we can of course do the same for the puts. So we collapse the calls association and expand the put association. Same thing, right? Here's the 70s, and then down here at the bottom is for my 90. These are the put prices for the 90 strike, right? So it allows you to selectively drill down and explore things in this tree. I think the Horner form is a good example of a nested expression where everything is subject to nesting. So I literally, in order to go deeper, I have to always expand a new level, right? This is by design. What makes the Horner form so interesting is that we always perform the same operation when we are computing this polynomial. You see that we always do x plus 1 and the result is multiplied with x. Then we're adding 1 and the result is multiplied with x. We add 1, the result is multiplied with x. So this is inherently deeply nested. You see that there's never anything on the same level, right? The whole thing goes to the right in a diagonal. So we never have anything on the same level. Everything that we are going deeper has to be on a new nesting level. Okay, so that's one thing that's worth noting about the Horner form. You see here how nested it is. Okay, how about a rather involved power series? You see that here we have a power series for the tangent. We are evaluating it at 2 and go up to a level of 6. So here's our power series expression that we can now explore. Here you see the tangent of 2, that's what we have here. And we can now dig deeper and explore the structure. And we don't have to look at everything because, as I said, we can be very selective and go deeper based on the branch that interests you, right? A branch in a tree is again a subtree, and the whole thing is therefore designed recursively. And I'll show you this in a moment, right? It allows you to be very selective. I find this quite useful. And things can get quite involved for larger three-dimensional expressions. When we look at this, for example, a rather involved three-dimensional expression is a graphics complex, and it gets big, right? Here you see numbers in the graphics complex with various lists that are on the same level, right? These lists here are all on the same level. That's why you see them here vertically under one under the other. And you can, well, interactively get in and out here, zoom any way you want to go into this, any way you want to explore this further. Right? You have vertex normals, and again, these numbers that you have there in this huge graphics complex that consists of several different heads and sub-expressions. All right, so note to self, show the expression class in Java and the recursion. So let's look at how this is actually done in Java. And I apologize if this is so blodgy. I think this is a ridiculously big font, but everybody tells me always in the feedback that I shouldn't make my fonts too small. People can't read my fonts when they're too small. So that's why I use these ridiculously big fonts for today to show you this. So this is Eclipse, and this is now the JLink utilities class that I've mentioned before, and here's the implementation. So to begin with, for the JT tree, I want to point out mostly that it's used recursively because the tree is a recursive structure. A tree basically consists of subtrees. Every subtree, again, is recursively defined by having another set of subtrees, all the way down to the last leaf. The end of a tree is called a leaf. So every tree is by design inherently recursive. And we see that here. I'm not going to explain everything in that, but you see that recursion is inside of function, and at the very end of function I have recursion, and recursion also has function. So this is how this is done recursively, right? Function contains recursion and recursion contains function. Next, I want to explain the expression class, right? I have a JLink expression class L, and L is a wonderful class that we have in JLink because it allows a lot of manipulation or a lot of functions, a lot of expressions that we are used to in the Mathematica side, now using on the Java side. For example, AtomQ is something you probably are aware of. You know that AtomQ there exists in Mathematica. There's also a head, right? So we have a lot of functions, not everything, but a lot of Mathematica functions that we now have on the Java side. For example, AtomQ question. I do this here because I have to have a distinction between a leaf and a node that itself has subnodes as subtrees. And we have head that we have here, and then toString and so forth. Right? You see that this is a head function of the expression class. And this is quite impressive and important. Let's look at the methods that we have in the expression class. And you see here that we have a lot of functions that we have in the Mathematica side as well. We have array, we have big decimal, big integer, double, we have AtomQ, we have complex, we have the dimension function, we have head in Mathematica, integer Q, we have length of a list, we have list Q, we have matrix Q, and we have some things like notify that we have on that's for event management. So I'm not saying that everything here is a Mathematica function, but we have a lot of Mathematica functions that are in here. Notify is not one, but we have a lot of them. Number queue, part, right? We have part in Mathematica, rational queue, real queue, symbol, string, vector, and so forth. Okay, and I encourage you to look at the Java doc. We have the expression class that we have directly available on the web as well. Here is the link, and I encourage you to look at it and explore this further. Okay, so this is what I wanted to mention here. We use the head here. I use that AtomQ and part. This is really all I need for the recursive definition of the tree structure for the expression. Okay, and then I've wrapped this together in a JT tree. There's a couple of things that are needed, stuff with that have to do with leaves and with icons and so forth. But basically, this is just a matter of formatting a tree. And I start that here with rec at the very beginning. That's the starting point for the recursion, with the expression that the user wanted at the top. And then we are iterating over all the nodes that we have here. Okay, so this is what I wanted to point out here for the expression class and the recursion of the JT tree. And next, let's go to some other examples I have used. People have asked on Stack Exchange. For example, here is a question from a user who's asking for a programmatic way to move the cursor to a desired location on the screen. So here's the link. I have the highest rated answer in there, and I do it as follows. I load the robot class and I instantiate a new one immediately. So I have a robot class now as a new instance, and I'm now moving the mouse. And look in the top left corner, you see that the mouse is moving something like an infinity symbol, right? Like a 8 that's tilted by 90 degrees. Okay, so let's look at this again. All I need to do is use the robot class and then call the mouse move method, and I do this as a table with numbers that are going from 0 to 10 pi in steps of 1,000. Okay, so here you see that this is Mathematica code that uses the robot class to move the mouse. You see that in the top left corner doing some kind of infinity symbol. Okay, the next one is the progress bars. And again, here is a link to Stack Exchange. Again, here I have the highest rated answer. Somebody asked, how can I change the color of the progress bar? And I've written a function show progress bar. I'm not gonna explain everything here. And I also have a function destroy progress bar. Again, I'm not going into all the details here, but that now allows me to use the progress bar directly as a swing window. So for example, in this one here now, I do a ping pong. Whenever the numbers are increasing, I say ping. Whenever they're decreasing, I say pong. And you see, okay, let's do this again. You see this also with a percentage number in the bar. The bar is changing and the title is computation progress. Okay, so in the next thing, I want to specifically answer the question about a red progress bar. That's what the question asks in Stack Exchange. I need to do again a reload of the look and feel, and here I can then set this to be red, and you can see that I now have a red color in the progress bar, and that uses the nimbus red as the particular color in the nimbus look and feel. Okay, and we can also use it interactively, for example, with a manipulate and a really bright color. So I do this with a Java new AWT color where I'm using 255 and 0. So look how bright this this bar is. So I think this should really satisfy the poster who is asking about a red progress bar. And I want to be able to use a manipulate here. And I had already mentioned that I use HTML formatting as components in these swing elements. So for example, when the slider is above 50%, then the title says upper half of risk. Okay, when I go below 50%, then I see lower half of risk in the title bar. And if the numbers are going above 80%, then the text goes red and boldface and says high risk. If I'm below 80% but above 50%, then it's normal text, normal risk, but upper half of risk. If I go a little bit below 50%, then title says lower half of risk and normal risk as the text. And if I go below 20%, then I have green text that says low risk, right? These are just very easy to do and easy to format these things with HTML on swing components. And we have a show progress bar indeterminate. Again, I'm not explaining too much, but I now can also have an indeterminate progress bar, and it continues to be in an indeterminate state until there is more progress. So in that case, you would destroy the progress bar, and now that's gone. Okay, so that brings me at the end of the first part that shows the use of the pointers into the JVM from a Mathematica session. The other way, the second part, is that I want to show you the other way around. I want to show you that I can use Mathematica from Java. And for that, let's go into the Armor class. And okay, wait, let me close that. So here we're going the opposite direction. So here we're using Java code and we want to call into Mathematica from Java in order to do certain computations or visualizations. So we need to load a couple of things from the JLink class. I need an expression, I need some link classes. The standard is typically the kernel link. There are also two others. There's also a math link interface and there's also a math kernel link interface. Okay, so there's a kernel link and there's a math kernel link. The math kernel link is usually not used that much. The standard is typically just the kernel link. I find that is the most flexible and I focus on that. I completely skip the math kernel link. If you insist on it, I can talk about it another time. I don't find it as useful as the kernel link. So when we are running through this, then we are creating a kernel link and we are using a create kernel link method on the mathlink factory with a couple of parameters. The important thing is that the link name is the executable file at the correct location in the executables directory, and here for version 12.1. We have to discard the first couple of stuff that comes immediately, and once we have that, once we have the kernel link established, the KL, we can now call, for example, the evaluate method, and in the evaluate method we can use any Mathematica expression as a string. Doesn't have to be a string, but it's quite convenient and it's one way, perhaps the most convenient way to use it. Again, then as the next one, we have to say wait for answer, because this is link based, right? This is, as I had mentioned in a previous session about mathlink, it is based on a send receive method. First, I have to send out the request to compute something, and that's done with evaluate of something, with something being a string of a Mathematica expression. Well, we don't know how long it takes, right? It could take 5 minutes, so we have to wait for the return, and we need to block at this point. We don't want any interference on the link, so we have to say wait for answer. But then when the answer is there, then we have it and then we can continue it, and then we can read the answer from the link in different types. In this case, I read it in as a string and then I assign it to S and then I print it. Okay, it doesn't have to be a string, and it can be many different types. We can, for example, integrate something. This is now typical Mathematica code provided as a string. So this will integrate the sine function from 0 all the way up to pi over 2, and we're getting the number back as a string. But we don't have to use it as a string. There's other ways to return the numbers. If it's numeric, then we can read it as a double, or we can read it as a integer. And in the next one, let's compute it as an expression. So in this case, let's use dsolve value. That's just a typical Mathematica expression. I'm asking for y prime of x is x squared plus 1. The solution is the tangent function, and the tangent function is an expression. It's not a number, so we can't read it as a string, not as a double. We cannot read it as an integer. We cannot read it as an array. It's a tangent, that's a symbolic expression. So we have to read it as an expression, and then we just can print it, and println prints it now as a string, right? So the output is going to be a string, but the return from the link was an expression. Okay? And here we are using a range of 20. I want it back as an expression and then I print it. The next one is range 20, but now I want to have it as an array, right? We have it, range of 20 would give us a list from 1 to 20, and what I want to have back is now an integer array, because that's really what it is when we are returning this. And the way to call this on the link is now get integer array, and the one means one dimension. It's a one-dimensional list. Okay? But then I have a little bit of a problem printing it, so what I have to do now is use the arrays class and call the toString method on it, and as argument I pass intArray, which was the return of the getIntArray1 method. So again, I submit the request for range 20. That is a list of 20 elements in Mathematica. I want to read it back as a one-dimensional integer array, and then I print it. Okay? I am now querying for a two-dimensional matrix, for example the Hilbert matrix of 5, and I numericize it here. So it's the numerical version of the Hilbert matrix of 5, and this is two-dimensional now. And what do? I use the get double array 2 because I want it back as a double. It's a real in Mathematica. After using n, it's a real, and I read it back as a double because that's how I represent the reals in Java, and I want it two-dimensional, so it's get double array 2, and here I have my two-dimensional double. And I now have a problem again printing it, but there's the deep toString method in the arrays class, so that will also not be a problem. The next one is a bit more involved. When we're not restricted to just submitting one Mathematica expression that evaluates to something. The compound expression is also an expression in Mathematica, but that means we can use the semicolon. So I can use a equals 5, b equals 6, c equals 3, and then add those three together. So get this back as an expression and print it. Okay? And in the following I do the same, except I read it back as a string, because this has a meaningful representation as a string. That's not always the same with an expression, but here what I query for is the very same thing, but I get it back as a string and then I print it. Okay? In this case, the result is going to be an integer. If a is 5, b is 6, c is 3, and I add them together, then the result is an integer. It's 5 plus 6 plus 3, but that's an integer. So here I'm reading it back as an integer, and then I'm printing it as a sum. Okay? And we can use arbitrary expressions. We can use whatever we want. And here again, I use the sum 1 over n squared from 1 to infinity. And this is now an expression, and I read it in as such. And another thing I want to point out, that I can also make definitions that way. So I can store the result away. That's why I call it store. And it doesn't disappear, right? Just because we're done with the links, sending out and getting back, that doesn't mean that the kernel disappears on us. It's still the same kernel. The kernel hasn't changed. The kernel hasn't disconnected. So we have really defined store to be an expression on the kernel. And just because we're done with the link stuff doesn't mean that the assignment disappears on the kernel. It's now in memory in the kernel. And in the next request, I now use the numeric version of it. So this proves that we made the definition in kernel memory, we stored it there, and here we are retrieving it back. And given that it's numeric, I have to read it back as a double. Okay, so this is pi square over 6 as a double. All right. Next, when we do this, then the next logical extension is that instead of writing multiple statements here in the way we would normally make definitions in the Mathematica kernel, is that we put this in a file and then we just get them. right? Get is a symbol in Mathematica. Get file name join is the way we construct the full path to the file, and get reads in the file, assumes it's valid Mathematica code, and then evaluates what we have there, and we can now go further. Here's a semicolon, so I now go further. Some value is some value times 4.3, and some value is defined in my demo functions. And so is the function grcf, and so is the function nicf. Okay, so this reads in the contents of the file, and let me show you that. Here's the function demo functions. So I have grcf, right? That is a continued fraction that I'm setting up as a nested expression, and there is nicf, that's also a continued fraction that I'm setting up with a nest, and I'm defining some value is 67.89. So grcf and nicf are functions that I have defined, pretty much standard as you would in a normal Mathematica session. These functions stand for golden ratio as a continued fraction, and this is Newton iteration as a continued fraction. That's where grcf and nicf come from, right? These are just sample functions. There's no rhyme or reason to that, but if you look at this closer, you see that this nest is the Newton iteration that computes the square root, and grcf is the golden ratio that we use with the convergence process as a continued fraction. Okay, so we can now compute these things. Here we are reading it in, some value comes from the file, we modify it, we compute grcf, nicf, we're adding some value, should give us a double, and that's what we are reading it in. And finally, a way that allows us to put expressions, in particular variables, from the Java side into the Mathematica side is by using the put function that is inherited from the mathlink interface, but now it's in the kernel link interface because the kernel link interface inherits from the mathlink interface. And we have to say that we want to evaluate an entire packet, and we are setting AAA, that's just the function that the variable name that I picked, and we put the value variable 1, which is 111, and this makes an assignment on the Mathematica side. The result is that AAA is 111. So this may seem trivial, but keep in mind that variable 1 comes from the Java side, right? We want to have Java variables that are now on the Mathematica side. I do the same thing for a variable BBB, and this is now a double. So variable 2 is actually 222.222. Okay, this is the important item here. We have an integer in Java and we have a double in Java, and we want these values on the Mathematica side. And this is the way to do this, right? You use set, right? And set is the equal sign that we are used to in Mathematica. And we set then now comes with two arguments. The first one is the name and the value, and that's it. And in the next one, we can evaluate AAA plus BBB. The result is obviously a real number in Mathematica, so we read it back as a double. Okay, so now let's run this, and we see the results are here in the console. So let's scroll this a bit. So here was the first one, 6 minus 9 plus the numerical version of pi. So you see this is pi minus 3. The next one was the integral of sine of x from 0 to pi over 2, and that is 1. Right? This is under the sine curve between 0 and 2 pi. Pi over 2. The next one is the solution of this differential equation, y squared plus 1 to be the first derivative, and the solution of this is the tangent function, right? It's the tangent of x, but we have to add the constant, so it's actually tangent of plus of x and constant 1, right? The general thing is this is the tangent of x, but we need to have the constant here, so that's why we have the plus in here. The next one is the range of 20, and the range of 20 is here, and I remind you again that this is done as an expression. So we see it as an expression here that is printed as a string. So now I'm doing range of 20, but I get it back as an array, and you see that this is the formatting of an array in Java. You see that this uses brackets and not the braces, right? This is the string version of a list because it comes from the expression, and this is the same thing, but now it's a Java array, and this is printed with brackets. All right, the next one is the 5x5 Hilbert matrix, numericized, and we read it back as a double array in 2 dimensions, and you find that here. You see the double brackets at the beginning, and here's the 2-dimensional Hilbert matrix. We can scroll all the way to the end. Here's the double brackets at the end. So this is what we get for the Hilbert matrix as a 2-dimensional array of doubles. Okay, next one, we had these multiple symbol assignments. They're done as symbol assignments with a Mathematica string, and I get it back as an expression. I get 14. Here I do the same thing, but I get it as a string. We get 14. Here I do the same thing as an integer. I get 14. Okay. The next one is that we want to compute the sum of 1 over n squared from 1 to infinity. We get it back as an expression, and we get times of rational 1 over 6 power pi 2, right? So this is pi square over 6. The input form of pi square over 6 would look exactly like this. Times of rational of 1,6, power pi, 2. This is pi square over 6. And again, I remind you, we store it away in a variable store in the kernel so that we can use it later. And here I retrieve it, I numericize, I get it as a double. So here's pi square over 6 as a double. All right, it's a real in Mathematica, it's a double in Java. So here we have this combination of reading in a file with get, interpreting it, multiplying some value with 4.3, adding the golden ratio done as a continued fraction with 45 and 8 terms, plus added the square root of 84 done as a Newton iteration with 12 terms, plus now adding some value, and this gives us something like 293 plus some change. And the last one is that we are using variables in Java that we now transfer into the kernel, right? It's the other way around. All the examples above, we computed in Mathematica and retrieved it as Java variables, and here we're doing the opposite. We are starting out with Java variables. We put them in the Mathematica kernel, but once they're there, we can, of course, get them back and display what we have here. So this 333.222 is the 111 plus 222.222, but again as integer plus this as a double. All right. Okay, so this brings me at the end of my session today. I hope you had as much fun as I did, and I hope you will use plenty of J-Link in your future career. Hope to see you next time. Bye bye.